interaction, how we can understand them, jointly by using the scientific constraints applied to the foundation models. And finally, based on the pros and cons, we can give some, summary and also the outlooks. So let's get started with what is ecohydrology. I cannot say I understand it very properly, and obviously we have a very strong group within CSIRO, specifying the ecohydrology. But so that's actually like a journal from the widely called ecohydrology. So from my understanding, you can say it's like kind of a composite of three terms. So ecosystem, water, and understanding. So from my understanding so we're using the research method to understand how water is interacting with the ecosystem. That is ecohydrology, in my view. And then based on their journal scope, we can say it seeks to increase the interdisciplinary insights by placing particular emphasis on the interactions and associate feedbacks with the space and time. So that is the remote sensing data, right? So Earth's observation, space and time. So we can do the research and understanding of the ecological system with the hydrological cycle. And by talking about the Earth's observation, across the space and the time, how do we use the data, EO data, to understand them? So, and also search there from understanding, you can see as I put my discussion notes to the ChatGPT, and as a base, there are some actually pretty good. I mean, as in my point of view, it's kind of like a process chain. So we're using the EO data. Obviously, we have like a strong cohort of remote sensing researchers here. We see the input data from, very early from the remote sensing. They use some spectrum bands. For example, the valence temperature or the multi-spectrum different all these bands. And basically, we build up some retrievals or some indices, NDVI, for example, very simply and reports, to understand some environmental variables. With, for example, always say, NDVI is like a proxy for the greenness, but that's kind of just based on their, some assumption of their absorption values, and NDVI actually has been demonstrated. Probably not that robust in many cases, such as, for example, in the crop growing or the harvesting stages, so usually saturated. But that's just a way to help us to understand this kind of the process. And then by building up this remote sensing data in the product of the retrievals, we can go to understand the states of the real world, which is very noisy and full of the uncertainties. Then we can, for example, also by integrating some of the ground observation data such as FluxNet, so water flux and also the CO2, all these flux that integrate together to make our decisions. So that's how the EO data is helping us within this process. And we've been in an era, probably you're not surprised, so where the EO data archive is exploding. It's not just about how many satellites we have seen from NASA or ESA or even Ecohydrology in Australia going to be launched, hopefully. But also, we see the data volume, and especially the archive. So you can see they are exploding every year, and it's kind of like an exponential increase. Being for their volume. And especially, the petabyte means that 1 PB is kind of 1,024 terabyte. You can imagine 300 petabyte data, and this is just for until 24 data. So you can imagine how big data volume we have had right now. So by integrating all this, very abundant data, I think there have been a lot of frontier researchers. They're doing their data-driven. For example, I think probably been for us. Many deep learning remote sensing studies. But mostly, I think their logic are all kind of the same. So it's kind of we have this input data from either the satellite data or drones or proxy sensing or with ground flux tower observation data, and kind of we build up either the deep learning or the machine learning models. Could be the tree-based or some more advanced, such as a vision transformer, or spatial temporal, LSTM, or convolutional, this kind of architecture. We can doing our proxy of this of these products built upon the data-driven method. And I would summarize all these kind of the products that built upon this data-driven method. They kind of the proxy of proxy. So the first proxy means that we're doing the modeling. So we don't know how these models are working. I know they are very good and also probably more advanced than some inaccuracies, more advanced than some process-based modeling. Like but it's kind of black box model. We don't know how they work, and then build upon some assumptions. Cause I'm not sure, but in many of the training, we train the response variable already being some proxy from existing data. For example, the UR5 is already being some reanalyzed, but it's being used very extensively as an input into the machine learning deep learning models. It's another proxy. And then also we see we can have many highly accurate data products derived from such method. The decision here, because the climate is changing, we've been seeing many more extreme events, more frequently and more drastically than previously we have seen. But this kind of transformer base, they tend to predict some, on the average. So the problem is a little bit weak in the unseen scenarios. So we still see there's need to advance with understanding, not only just using this data-driven method. And by in a little bit more with the proxy of the proxy, we can see using the soil moisture, which is like a important variable in the ecology. This is like work we did in last year, in Brisbane. And basically, we see is kind of like a retrieval mode for either the microwave, passive microwave, for example, the soil moisture active passive, like the launched by NASA, or by the Sentinel-1, which is more about the active microwave launched by the ESA. The kind of we see as they did not directly observe the soil moisture quantifications. Rather, they're using some retrieval model to inverse either you can say in the microwave, passive microwave, it's about the actually constant or the scattering from vegetation or the soils. They reverse them into the soil moisture estimates. And even more complex in the ecohydrology, because soil moisture is usually only the first step. But even a bit more, this is like our research from the University of Wisconsin. You can see it's kind of the process-based model. So they're trying to simulate the ecosystem and derive all this, like a proxy chain from the solar radiation and then going to the CO2 and also the absorption, the photosynthesis, and then could be the respiration during the night, and all this kind of the proxy of the chains. I guess that's kind of like a motivation and also a reason we have been thinking about how we can refine this understanding and using the data-driven method like we just mentioned before. And just like we mentioned before, even with the very advanced, the SOTA example of this data-driven, for example, this is like an extension of the FluxNet, which is more about the CO2 and also the water flux. Globally, as built up by a team in Germany. They kind of training on the global flux tower data, and then they build up on their extreme gradient boosting to derive different states of their water or CO2 carbon fluxes. But as we say, what if they're being applied to the unseen scenarios? For example, there is like a extrapolation. Extrapolating from this flux tower, so I might just use my mouse, it's easier, sorry. We see the flux tower wave, we extrapolate this kind of the same conditions to, for example, mountainous region, which has always been like a challenge in the remote sensing. So the radiation series, for example, the RTM, radiative transform modeling, usually does not work in the mountainous region because of the elevation and also their topography. And with only the flux tower knowledge can be really derived some, reliable and also scientifically sensible products, even with very advanced technologies such as the X-phase. You see there's distribution seemingly plausible, the gross primary productivity for the global, but we can conceptualize there are many areas they being unseen, they might be inapplicable in this case. So by seeing that, I think that we've been summary the eco-hydrological process as like a proxy and the EO data must be built upon some, robust and also like a proxy chain to help us to understand how the water is interacting within all this process. And this is another AI figure. I acknowledge the use of AI in this case for summarizing all this kind of the proxy chain. Actually, this can be like a good example about how this either the data-driven or the AI method, they help us understand this proxy chain. My understanding here is actually they do not understand this kind of proxy chain if we, did not explicitly indicate or tell them. Because we see also give us some fancy or very scientifically vivid icons, for example, of this. But if we look at the arrows indicating the interactions or the proxy chains, we probably see some of them might be a little bit confusing, the chain are reversed and also maybe in chaos. So still they probably be good in predicting all this or understanding all this status, but still all interactions they might not. And there's another example from our last year work in TGARS. So this is for the soil moisture prediction. And I'm sure many of them been using the very commonly used SHAP, the Shapley values. So we can see in our previous work, we probably can see some limitation about if we want to do the soil moisture prediction. In this case, here are like a list of different kind of the top predictors we've been used within the machine learning. Although SHAP help us to understand this interaction a little bit, but still within the machine learning framework, right? So and also this is really like a cycle for this the variables. For example, we see the evaporation amount, one of the most important variable here. It probably makes sense because it's relevant to the water status in the soil. But does that fit into the proxy chain? For example, that means soil moisture is probably coupled with the evaporation, but it can be really determined based on like a machine learning model. So how they contribute to each other. I guess it's still a front-end complex problem which hasn't been answered in this case. So it's kind of some background for the eco-hydrology and how we've been so far. The understanding and also doing our modeling, the data-driven modeling to predict the kind of ecological variables. In this case, are there any other possibilities to refine either our understanding or maybe more basically refine our the applicability? This is where we introduce the Earth observation foundation models, which was probably just like a very new concept with like 2 or 3 years before. So in this section, we see the EOFM, Earth observation foundation model. They're probably going to provide us with a new opportunities for the representation as there is physics. Let's say what is an Earth observation foundation model? As we can see, the real world, all the observation from remote sensing, they are quite noisy, right? So there are lots of dimensions here. We probably don't know for example, if we want to concatenate all this kind of the Landsat, Sentinel, and also even some commercial like the CubeSat and the reanalyze the land cover data information. We as human probably cannot understand as them very unified, but I think the EOFM, the concept is that what if we can train a machine learning or like for example, I think they mostly use the transformer or like the spatial temporal former to integrate data as much as they can. So I think it's probably relevant to their scaling laws, belief. So if we can train all the data, we can see some emerging or the evolution of the capability of the model. That's also kind of the the foundation model is meant to. For the Earth Observation Foundation model, this is like a paper by Dr. Xiaoxiang Zhu in this year's Communication, Earth and Environment. And we see as we trained all this kind of very abundant exploding data in like a physically consistent way. This is, for example, this is a Navier equation, which is for the build it, and then we can build upon like a model to be unified, which they call embeddings. I will introduce in the next slide. And this kind of the embeddings, the kind of the highly compact information, concatenated all this kind of the different very noisy real-world data into some reusable representation. It can be for thermal, for soil moisture, for water, for everything. We just did not have like a very good understanding of them so far. And for like a SOTA example, must be the Google Alpha Earth, which was introduced by the Google DeepMind in the last year. As you can see, this is like a illustration by the Google DeepMind in their archive preprint. Actually, probably like a work report, but put on the archive. So their philosophy was to harmonize and summarize. So harmonize the things we want to harmonize all this very noisy data into something like a unified, like a georeferenced, temporally consistent, and also summarize all this noisy information into 64 dimension in the Alpha Earth case. And also, this year, we want to use this useful embeddings 64 in total to accommodate different data sources and also streams. So it can be like segmentically meaningful concepts. I know I'm not sure how audience background, but from my understanding, this is a little bit more computer science oriented. From my understanding, so it can be they can be classified into different types and also meaningful in this kind of the types. Sorry, I'm not really limited in this computer science understanding interpretation. Forgive me here. But yeah, finally, I think their conclusion of their the argument they want to make. So all this kind of representation, so they train all this data, it can be easily reused, and also they minimize the need for the complex process-based modeling, which can be very computational intensive. And here is like illustration from Google DeepMind about how the Alpha Earth, the embeddings, how they look like. Actually, pretty cool. Actually, I was impressed, by all these kind of the RGB composite and also how they can be used to represent the land features in this case. But still, we probably do not understand what they really represent for at this stage. The philosophy we probably can interpret a little bit. We say all these input data will be very familiar in the society, the GIS society, this Landsat, Sentinel, and also they just being all embedded into what they call like a teacher model. So the teacher model is equivalent to the foundation model here, and that is their philosophy. So if we can use a pre-trained, a very large model to learn this, multi-stream, model information in remote sensing phrase. Then it can be something like a teacher to teach, the students, which can be very downstream. For example, like a simple random forest or extreme gradient boosting, the classifier or the regression model as a downstream here. So then I probably want to ask what can this? Because different teachers, they have different philosophies, right? So their teaching style is actually can be quite different. But in this case, I think for the Google DeepMind, they've been trying to convince the users we can, the philosophy of the Alpha Earth can be focused on this kind of the different streams. For example, the similarity search, classification, regression, and also the change detection. And in today's talk, because the regression is really a way to predict the spatially, temporally continuous data. So so much all the water and carbon fluxes is relevant to the ecology. We're going to show you some examples to see if they are convincing enough. Decisions too. Here's an example. Still very fresh. Last year is an example of the applied the Earth observation embeddings, FM embeddings to the vegetation water content, VWC, published in Remote Sensing of Environment. This is like agricultural case. So so we got like the soybean and also the corn in their different technology stages. And so predicting such the vegetation water content can be quite tough actually, right? Because the IEEE has been known for its saturation problems, especially could be like in this near harvesting stage. So the kind of we are going to be saturated to just one, but we did not see more variations in their data. So the radiative transfer model has always been questioned a little bit in this kind of different vegetation phonology stages. And I think that the argument is that by probably not replacing, but by proposing like a new method, can we use like the unlabeled data rather than I think could be to some extent biased radiative transfer model. Can we use them to improve the kind of the vegetation water content estimation in this case? So we just drop all the assumptions and using unlabeled data from the Earth observation embeddings. And their results, I'm not sure if the R-square is convincing enough here, but this is what they reported. So they can achieve 0.9 for the R-square for soybean and corn. And also this is for the vegetation water content, and then nearly perfect 0.95 and 0.98 for the crop height. This is trying to demonstrate it can be using as purely data-driven to be competitive and even better than the traditional proxy chain-based the models. And another one is more relevant to the water flux, the evapotranspiration. This is like open ET project. So I think SAR also have a national actual evapotranspiration of the sunset within CSIRO. So they're trying to estimate Australia's water loss at a monthly centimeter step. OpenET probably like a similar, a more ensemble approach. Google DeepMind, their argument is that what if we can use this kind of ensemble means of the OpenET evapotranspiration, the water loss across the United States can be reproduced by using much less and very minor training samples. Because this kind of information has already been learned by the teacher model, the foundation model. Can we use as a more computationally efficient model to reproduce? And their argument, you see, this is the small text. Their general argument, you can see it from here. This is the Alpha Earth foundation model, and this is probably the R-square improvement compared to their input of the evapotranspiration ensemble mean. This just demonstrates this much. The improvement in the R-square in prediction, and as they compare to some ground truths, for example, this is Alpha Earth predicted evapotranspiration for a paddock by using very minor data, which is very computationally efficient. By comparing to either ground truth and more this is a sentinel image, and also it's a ground truth. We can see some sensible pattern and showing some physically plausible spatial patterns from their arguments for the water loss in the paddock. And what they're trying to deliver is that because if we can using this such much more less data, we can produce relatively accurate proxy of this ensemble mean. So it can be demonstrated going to have a larger extrapolation capability over some kind of the large spatial extents as an argument. And that's just for the Alpha Earth from the Google DeepMind. And here is just probably a little bit overwhelming summary of this recent 2 years, how many Earth observation foundation models we have so far. You probably don't want to read into details, but you can just have a look. About their publication year, mostly this year and also last year. So it's kind of an emerging area. So researchers are trying to explore how they can be adapted. We can either have different input sources, different architectures, and also they can have different roles. The teacher model, they can be different in how they're learning and teaching the downstream tasks. Basically, simply, in summary, they all still vary in their spatial temporal resolutions. I think that this probably still very common in all the remote sensing variables and also phrase. We can see they can be either multi-spectrum, for example, can be either only for the RGB represented in R, and also all the multi-spectrum, or either it can be more multimodal RGB multi-spectrum, and also with the star capability, and also even more. I think the DOFI was proposed in this year, from my memory, might be wrong. So even with some hyperspectrum capability, they're trying to build into more and more data to be embedded into the Earth observation foundation models. But they still have this kind of the scale, capability of the applicability. Even compared to the climate model, we still see probably with this kind of UFMs, we can apply or implement into relatively abundant information to finer scale or finer resolutions, which can be down to 1 meter, as demonstrated here. It's probably a similar philosophy about in soil moisture, because I did lots of research in soil moisture, so this is my preference to give an example. We see so could be with such emergence of this very abundant, lots of choice of this Earth observation foundation models. We probably want to make some choice. We want to make some benchmarking, so to say which one is more applicable and also which one can be more useful for a specific tasks. That's probably the argument here. Just like in soil moisture, we see we have all these different sensors and also the missions of their applicability can be varying, especially if their target is varying with the spatial and also temporal resolutions. This also applies to the UFM. So after introducing the ecohydrology and also the UFM, the concept and such abundant their choices, we also have want to how we can do some interactions, how we can constrain them. In the ecohydrology context, how we can constrain this UFM to probably better refine our understanding. So let's just revisit the UFM archive. So we see still this is a Google Earth architecture. We see input, what they've been learned as a teacher, or what they output to be taught to the students, which are the downstream, relatively simpler machine learning or deep learning or regression or the classifier. So my understanding so far, so we can either adjust the input, just like we see so far, in the last slides, adjust inputs such as ranging from the multispectrum to even hyperspectrum, the information abundancy to be embedded into the teacher model, or so we can let the teacher, they change their teaching styles, which I will give an example. And just for a quick illustration, this is another AR figure, but I think doing some good summary after my verification. We see this is the inputs. Can we maybe give more unified information, or do we want to provide some more specific, only for one task, extra level constraint task? That can be debating. I can foresee probably in next few years. Or we can constrain their outputs to be more physically plausible, or consistent with the physics in the real world, and can be more reusable with the eco-hydrological the phrase. So I will give examples to each task, either the inputs or the outputs. So for the inputs, by refining the inputs to the teacher model, the Earth observation foundation model, there can be a few candidates as to refining or harmonizing the inputs. To make the inputs already being more spatial temporally consistent. This is a spatial temporal fusion technique proposed by FUNGAL at the USDA, which stands for United States Department of Agriculture. The idea is we got this multi-stream data, for example, from MODIS and also Landsat, they either sparse in the coarse in the resolution or sparse in the temporal frequency. So we actually can do some pre-processing to make them like the spatially temporally information abundant. That is what we call like spatial temporal fusion. So by doing some pre-processing to increase abundancy of the information to be embedded into the UFM. And we also did some work in 2023. It's also still about the refinements can be embedded into the fusion process. For example, some bias correction locally and the jet. The already inconsistency in this very abundant, noisy, and also multi-stream data. Or another one can be the more temporally frequent and also especially more continuous data, Himawari. This being the Geohydrology in Australia being in long-term collaboration with the Chinese meteorological agency for getting their Himawari data, so they can produce 2-kilometer resolution every 10 minutes. The data for the full disk cross. You can see here the first imagery from Himawari. And what we also did in 2024 is we can say that we do the harmonization to refine the inputs. So the general concept from here is that we already see the different products. If you can see this little bundle here, so a little small here. But they generally represent the different products. So this means that if we already have this kind of the multi-stream products, previously we input the multi-spectrum or the hyperspectrum information, right? What if we input this kind of the retrieval into this UFM? We probably need some harmonization and also to already reduce their inconsistency by especially in temporally high frequency, such as in Himawari, 10 minutes to give them more temporal context. After talking about the inputs, or what about the outputs might be adjusted to be more eco-hydrological applicable or the physically interpretable, which can be seen from a very recent study published, I think, just in this month from Peking University in Science Advances. So I think their argument is that none of the existing UFMs being very specified, their teacher model not very specified in the hydrological cycle across the globe. So what they've been doing is that, for example, this is what they call a remote sensing translator. So they're going to translate the teacher model's outputs, just another layer in the deep learning models, adding the translator to just output all the eco-hydrologically relevant variables. So if you still remember for the alpha Earth, they kind of output all these 64-dimension different embeddings which cannot be interpreted by the human. However, if by adding this kind of the translator, which can be within a Bayesian framework to be consistent with our human knowledge, it can be more directly useful into the hydrological cycle, which they show an example here. This is for the evapotranspiration extracted from their model called the BERS, bidirectional encoder representation from transformer for hydrology. So their promise here is that they can produce globally consistent from this foundation model, which is just directly reused for example, as a high resolution evapotranspiration, so which can be both consistent with their input spectrum information and also the downstream hydrological, the physical knowledge. And here are some examples they show. We'll just focus on this Australian example, where you can see in the 2023, roughly the September or August, the present burning, there are so moisture status as one of their variables output from their foundation model. Can be very timely reacted to the prescribed burning in their demonstration. And also, they also give some spatial examples for the cross-validation. And we've been thinking about for all these outputs refinements, building upon their the birds. This is like the birds that are advanced their UFM. Actually, can be also interacted with more process-based to be benchmarked and also cross-validated. For example, this is like our work we're currently doing at the University of Sydney. So it's more about also like the process-based evapotranspiration, and this is for the Luzon soil moisture. Either can be cross-validated with this outpost to say if they can make sense in the ecological phrase, their temporal phrase can, to be more consistent. This kind of benchmarking question. So then our kind of argument in this section will be more about we're starting to think about with current the UFM capability. We need to benchmark what operational ecological products or the understanding what do they actually need, and also we still haven't seen a very good benchmark so far. I think they are kind of emerging, but we're starting to think about how can we properly benchmark. Do we need like a larger, more unified model, such as, many computer scientists believe in the scaling law. It just can be doing things for everything. Or do we want to develop something more specifically, such as the kind of, the hydrological cycle foundation model? We're just only using for some expert research as very specific. It can be still going to be a debate, I suppose. And finally, is the outlook section. So in this case, I put our discussion notes with my colleagues into the ChatGPT. I think that's a summary for me. So I think that's kind of the outlook is that we see already the UFM they've been implemented and demonstrated some promises for all this segmentation or the spatial, the classification or the spatial tasks, but we probably, for the eco-hydrology, want to shift from the spatial maps to more about the mechanism, the temporal things. Because usually, if we want to understand mechanism in the remote sensing, it's about temporal information, right? So it's like a causality. Something happens, then lead to something later happens. It's kind of embedded within the temporal information, and that's probably which is late in the current UFMs. And we still need to iterate. So from all this pre-trained data, we need to adapt to this kind of very specific knowledge. We constrain them and we benchmark, deploy them. Finally, we still probably want to say if we can embed the newly observed or generated data, which is kind of an iteration cycle. So yeah, finally here's the summary. In this talk, we firstly introduce how we understand the ecology, which is basically about how we understand the water spatially, temporally interacts with the ecosystems. And we see that the Earth observation foundation model offer their process to be more easily implemented or interpreted by their promise. But many of them, although they are emerging, many of them they are still too new to be universally good, in my view. So a key challenge we have identified is how we can define the input and also the output from the UFM. Especially we want to constrain them by the physical principles of our process understanding. And finally, the benchmark still can be a very good. The future direction, and we need to distinguish between the lower constraints. For example, less temperature, which is some regression, or the higher, for example, the productivity of the photosynthesis, which kind of is a good about more process in this case. I also quickly acknowledge this work was supported by some funds from either the University of Sydney and also the Google Cloud. And also was supported by the NCL Australia. And a very sincere thank you goes to Dr. Yiqing Guo, Dr. Wen Jing, and Dr. Yang Chang Zhao for their invitation, organization, and host. Thank you very much. And finally, we want to acknowledge a special issue in the IEEE Geoscience and Remote Sensing magazine, which was initiated by the Dr. Xiaoxiang Zhu's team in TUM, which motivated us and helped us to initiate and refine this work. Thank you very much. Any questions and comments would be very welcome. Thank you very much.
If there are any questions?
Yeah, great presentation. We talked about, say, multiple data modalities and say how we transform them into, say, meaningful interpretation. But say, how about any thought process on transferring of, say, transfer learning put into context, where feature representation from one modality can help it cross into other modalities as well.
So you mean can we use transfer learning?
Can we use transfer learning in this context?
I think probably, from one thing we can, so I don't know how, but I think we can. So just like an example for Alpha Earth, I think that, if we see from their training data, so transfer learning can be either spatially or temporally, right? So I think that's the only trend on a few years, for example, from 2017 to 2021, from my understanding. I might be wrong, sorry. But by learning this year's data, obviously they can be used for either other forecasting of temporally transferable in this case. I don't think that's the spatial transfer learning would make sense in this case, because it's already been like a global trend model. So already, I think they extract they argued representative samples globally. So I think the transfer learning would make more sense in temporal, and also how can we see, for example, in unseen situations. I think that's where transfer learning can help. For example, more extreme events, if that makes sense.
Yeah, just a follow on that. I think it is a project to transfer learning. Yeah, very good. The contribution in that part. Yeah, great talk. Yeah, definitely. I think I'm glad you mentioned the magazine. You can put together your work and you publish there.
Thank you very much.
And also you have lots of connections. I think Xiaoxiang Zhu, Jeff Walker, all those people. And also you're involved in IGAS quite well. Yeah. Okay. So are you going to go to Washington DC this year?
No,
not this year.
We have to fund for the national travel this year.
But you went to the Greece one. At 24, you were the student ISIS. I see. Yeah, the finalists. Yeah, great.
Any more questions from the audience? For people attending online, please feel free to unmute yourself and ask your question, or just put your question in the chat box and I'll address it. Yeah, I've got a question that in remote sensing images, optical images, there's a lot of cloud. So I'm not so familiar with the observation from different models. So I'm just curious about how do they handle clouds in their modeling.
Very good question. I did not say the details of how they process the cloud actually. My understanding is that so it's kind of my understanding, so I might not be correct. So before that, first of all, you can use their inputs from the output, for example, sentinel-1, so to accompany them this kind of information. And because you see the teacher model, the Alpha Earth here, it is more about all the spatial, for example, the segmentation and also classification. I think cloud, if for this kind of spatial tasks, we observe things in, for example, in 1 month or 2 months, unless they undergoing very rapid changes. Otherwise, for example, we uncover segmentation of classification. So in 1 or 2 months, they probably do not change too much from my understanding. So in this case, as long as they can get the clear sky or near clear sky in this say 2 months period of time, so this can still be very useful for these spatial tasks. I mean, this can be a very good point because that's cloud definitely affects the information about temporal things, especially in Australia. We see as a drought, all the wildfire, all of the consolidated chain here. So definitely like how to call refinement points. So that's how we can handle these clouds and to increase the abundance of the temporal information. That's my understanding.
Any more questions? I've got another question here that, most of the remote sensing images, they are just time series images. But Bavaria is more like a video.
Video?
Yeah, it's recording images every 10 minutes. So, yeah, I'm not sure if Earth observation condition models, they can consider this type of input like the very high temporal frequency, but relatively low. In machine learning and AI, there's a lot of video condition models. So how different between Earth observation condition models and those can address video?
Actually, I think you just raised a very good point. Many of the foundation models, they are indeed vision former. So like when seeing the vision former, I think it's more about computer vision architecture, right? I'm not sure the audience probably have many computer science background audience here. So the vision former, they already been developed in handling this kind of video that you can see. And also in their video architecture, the temporal information that being used is their timestamp. So that's quite straightforward. If you have all this stack information, every of them, you have, for example, in SADF, so you have the timestamp, and the steps you can have a sequence of how video is playing. So actually, from my understanding, for all this some of the temporal condition models, they have already have the capabilities to handle all this information. But it could be integrated with the previous question. It's just more about if we see this kind of the very high temporal resolution videos, but we have doubts. Can we still expect useful information? But back to your video question, I think it already been developed as a vision transformer. So we already consider this kind of temporal sequencing encouraging as my understanding. So I see. I don't see that tomorrow it would be like a real in this case from my understanding.
Any more questions?
I'm sorry, I came in late. I don't know if you mentioned this at the beginning. I'm actually a headquartered weather economist. I price weather for farms. Are any models currently being deployed in the commercial, agricultural, commercial situation?
You mean the foundation model?
Yes.
I don't think so. Because that's
sorry, how old are the models? How old are these models? Is there first generation?
Yes, I think they are among the very first generations. If you see the papers here, we see lots of them. Yeah, I think the oldest one is 2022. But that one is more about. I'm not talking about this sector, but most of them they've been developed very recently. So I don't think they've been transformed into the commercial sectors. That's my understanding.
More questions? If not, thanks Dr. Yu for the excellent talk. And for those in the room, we've got some food here. Please feel free to have us. Thanks everyone for attending today's seminar. This is the end of the seminar. Thank you very much.